Hello everyone, this is Mike Dowding with the SD Mines Physics Department, and we're continuing with Chapter 29 material. And Chapter 29 is exploring the connection between how magnetic fields can be influenced by current carried in wires and vice versa. And in the previous video, we derived the expression for the magnitude of a magnetic field for both a straight segment of wire and a curved segment of wire. So for the straight segment of wire, the expression that we got was mu naught I over 2 pi r. And in this case, I was the current traveling through the wire, and r was the distance from the wire. And our magnetic field would then orbit around the wire, going into and out of the board at the two different sides. So our x with the circle indicates a vector going into the board. Our dot with the circle indicates a vector coming out of the board. And so our magnetic field is orbiting around that wire. We also had the magnitude of magnetic field that is produced in the center of a loop of wire, which is carrying current. And that magnetic field will pass through the center of the circular loop, which also has radius of r. However, the expression comes out to be different, first and foremost due to the geometry of the system. But when we go through and we evaluate for the magnitude of that magnetic field, the expression that we get is mu naught I over, excuse me, I'm looking at the wrong part of my notes here. Got to get to the circular segment. We have mu naught I times phi over 4 pi r. And phi is the angle in radians that we travel around the circular segment. So in the case of a full circle, phi would be 2 pi. And then we would plug in 2 pi for phi. And as a result, the magnitude of magnetic field within the full circular arc would be mu naught I over 2r. But if we start segmenting the circular segment, so maybe we only go for a half a circle, then we only have half of the angle, and as such we're only going to get half of the overall magnitude. So that's the basic review from the last video. And so now what we want to do is we want to take the magnitude of the magnetic field that is produced by a straight segment of wire. So that is our magnitude. And we want to see what happens if we put two wires side by side. So on the left we will have wire A, and wire A will have current A running through it. In fact, let's call this wire 1 instead of wire A. The book uses current A and current B, but I don't want to get things mixed up with the B that we're using for magnetic field. So we'll call this current 1 and current 2. And for right now, we'll have the two wires running parallel to each other, and so that means our currents are also running parallel to each other. When we finish with this discussion, we're actually going to flip one of the currents over and see if that has any effect on things. But for right now, both of our currents are running up, and because of that, each wire will produce a magnetic field. What I want to take a look at is if wire 1 is creating a magnetic field, how will that magnetic field affect wire 2? So the first thing we need to do is figure out when wire 1 produces its field magnitude, where is it going to interact with wire 2, and that's pretty standard. We could measure the distance between the two wires, and we could call that D. And that means that the magnitude of magnetic field that's being produced by wire 1 is mu naught I1 over 2 pi, and then we need to see how that field is affecting wire 2. Well, wire 2 and wire 1 are a distance of D apart, so we're going to replace R with D. Likewise, wire 2 is going to produce a magnitude of magnetic field based on the same equation but different current. And we want to know how the field from wire 2 affects wire 1, so they are also distance of D apart. The next thing we need to figure out is what direction will these two magnetic fields be pointing when they interact with the other wire. And for that, we can go back to our we can go back to one of our right-hand rules that says for any current and field expression, there's going to be a straight line portion and a curved portion to your diagram. And this comes from the curved finger analogy, where we take our right hand and we curve our fingers, and our thumb is the straight line portion of the diagram, and the curve of our fingers becomes the curved portion of the diagram. So with respect to wire 1 is traveling in a straight line, so that is the current, wire 1. And that means that the curved portion, when we wrap our fingers around wire 1, we're going to see our fingers wrap around in this direction because our thumb has to point up in the direction of the current. And so this means we have a current that is orbiting around, a field that's orbiting around our current in this direction, but it's not just at that radius. We can go all the way out to a radius of D, and that means there's going to be a larger path for that same magnetic field to travel. And so when field 1 actually intersects wire 2, field 1 is oriented into the page or into the screen. Okay, so I'm going to get rid of all that other stuff and I'll just keep the field orientation there. But then we need to switch over to wire 2 with current 2, which is also pointing in a straight line. which means that field 2 is also going to be curving around the wire, but I need to know how that field interacts when it hits wire 1. Well, if we make that field line bigger, field 2 is orbiting around wire 2, but it's actually going to be coming out of the page when it intersects with wire 1. So now we can see which way all of the currents are pointing. We can see which way the magnetic fields are pointing with respect to the two wires. And once we have a current that comes under the influence of some outside magnetic field, we can apply one of our cross product relationships that says anytime we have a current traveling along some length of L and that current is passing through a magnetic field, there will be a force that acts on that current, or in this case there will be a force that acts on the wires. So what we need to do is figure out what are going to be the respective magnitudes and directions of the forces that are acting on these two wires. And first things first, let's figure out the direction of these forces. The first thing that we should remember about any cross product is that the resultant vector in a cross product is always perpendicular to the two vectors that are used in the evaluation. So whatever direction the forces point with respect to these wires, they both have to be perpendicular to that force. So both the length and the magnetic field. Well, where are the length vectors? The length vectors are going to be paired with the respective currents. So I have length 1, which is the displacement through the first wire that current 1 has to travel, and I have length 2, which is the displacement that current 2 has to travel through its wire, except that I drew this in such a way that the magnitudes of L1 and L2 are the same, so I'm just going to call them both L. Alright, so next, now that I can see which way all these vectors are pointing, I need to figure out which way the resultant force vector is going to point. And let's start with wire 1. I want to know what force is acting on wire 1 as a result of wire 2. And so wire 1 has current 1 passing through a length of L, and it is under the influence of the field that is being generated by wire 2. So now our right hand rule, so another way of using our right hand rule, our right hand rule says that the first vector in the cross product is the index finger. The second vector in the cross product is our middle finger. And the result, or the resultant vector, is going to be our thumb. So when we look at wire 1, our first vector is the length vector that is pointing up. So take your index finger and point it up in the direction of L1. The second vector is the field vector, that is your middle finger. That is going to be the direction of B2, which is coming out of the board. So you may need to rotate your wrist so that you can point your middle finger up, keeping your index finger, your index finger should be pointing up. Your middle finger should be pointing out of the screen towards you. And so right now what we have is middle index finger pointing up, middle finger pointing out, and then without breaking anything, your thumb can only point to the right, and so that is going to be the direction of the resulting magnetic field. So wire 1 is going to experience a force pushing or pulling it to the right, or it's going to experience a force that attracts it towards wire 2. Then we want to figure out what's happening with wire 2. So force on wire 2 as a result of wire 1. Wire 2 has current 2 running through a length of L, and it is under the influence of field 1. So we come back up to our picture and we use the same cross product approach. We have L2 pointing up. So take your index finger and point up. But now the field is pointing into the page. So take your middle finger and orient that so that it's pointing into the page or into the screen. And if you're doing that properly, then the only direction that your thumb can point without breaking it is to the left. And so we get two forces acting on these two wires as a result of their interaction, and we can see that the two wires are being attracted towards one another by these forces. Now I had a key statement in there. I said interaction. And if we go back to Physics 1, there was a rule brought about by Newton. It was his third law that said for every force there is an equal and opposite counterforce. So if I have wire 1 being influenced by wire 2 with a force, and wire 2 is being influenced by wire 1 with a force, then these two forces should be equal and opposite to one another. And so far all we can see from our diagram is that they are pointing in opposite directions of each other. Is there some way that we can confirm whether or not these two forces actually have the same magnitudes? And to do that, or at least to start in doing that, we can try evaluating these cross products. And when it comes to evaluating a cross product, the easiest way is to take the magnitude and angle relationship between the two vectors. The two vectors involved are the length vector and the field vector, and then sine theta is the angle relationship. And so for force 1, 2, the magnitude of force 1, 2 should be current 1 times the magnitude of L, which is L, times the magnitude of B2, which would be B2, times the sine of the angle that exists between those vectors. So we come back up to our picture. L1 is pointing up, B2 is pointing out of the board. That angle relationship is 90 degrees. sine of 90 becomes 1. And so we get a magnitude of I1 LB2. That is the magnitude of force 1, 2. For force 2, 1, we have I2 times the magnitude of L times the magnitude of B1 times the sine of the angle that exists between those two vectors. L2 points up, B1 points into the board. That is again a 90-degree relationship. So our sine theta evaluates to a 1. And we get I2LB1 as the magnitude of force 2 as a result of wire 1. Well, these look very similar, except that the subscripts are in the wrong spots. I have current 1 versus current 2, and I have field 2 versus field 1, and that's totally to be expected because that's the way that the system is set up. And we might say, well, no, these two are not equal to each other, the subscripts are in the wrong spot, but we're not done just yet. We know that field 2 has an expression describing it, mu naught I2 over 2 pi d, just like field 1 has an expression describing it. We're going to take the magnitudes of these fields and we will plug them in to the equations that we got down here and see if that makes any difference. Alright, so for F12 we had I1L, and then we have to multiply by the expression for B2, which is right here, mu naught I2 over 2 pi d. For force 2, 1, we have I2L times the magnitude of B1. There's our expression for B1. It is mu naught I1 over 2 pi d. And now, with a little bit of rearranging, you can see that the magnitudes of these two forces are in fact the same. They both have mu naught, they both have I1, I2, they both have L, and they both have 2 pi over d. So that is the magnitude of both of the forces. The magnitudes are equal, and from what we've already seen from the diagram, the vectors are pointing in opposite directions, and so Newton's third law is in fact justified in this case. It has to be, otherwise we would have to go back and retake physics 1 again and redefine one of Newton's laws, which we don't want to do. Oops. Okay, so we have the forces that are acting on the two wires. They both have that magnitude. And what I want to do now is just consider when these forces start acting on the wires. So we had our two wires, the forces are going to attract them. These wires are going to start bowing in towards one another. And as those wires get closer together, what happens to the force between the wires? Well, as those wires get closer together, the separation distance becomes shorter, which means that that attractive force is going to become stronger. And one of three things could happen. One is that the wires will continue attracting towards one another until the tension in the wire no longer allows them to continue moving. The second outcome is that the attractive force between the wires could be too much for one or both of the wires. One of the wires might get ripped out of its connection points, or one of the wires might sever. A third option is that the wires might actually come into physical contact. So those forces continue pulling and the two wires actually touch, and hopefully the wires have some kind of insulative sheathing on it. Otherwise you could end up with some kind of a short circuit event. Now, as promised, we are going to take this system of wires and we're going to flip over one of the two currents. And what we can see from this example problem is that if we have currents that are running in parallel, the two wires will be attracted to one another. So what happens if we flip one of those currents over? Are they going to repel? Are they still going to be attractive? Could it be nothing? Could there be no attraction or repulsion? Well, we'll let the physics tell us. We'll go ahead and keep current 1 pointing up, but now current 2 will point down. Because current 1 is pointing up, the field that is generated by current 1 when it intersects wire 2 is going to be exactly the same as what we had before. Nothing has changed about current 1. These two wires are still a distance of d apart. I know we didn't put in values for the two currents, but we'll assume that the magnitudes of the currents are the same. It's just that current 2 has now been flipped to go in the other direction. So everything about I1 and B1 are the same, but what about B2? What about field 2? Well, we can see that current 2 is traveling down, and we go back up to the top of the page here, and for our, where did it go? To zoom out here so I can find the stuff. Maybe I erased it by accident. But by the same argument, we have straight line portions and curved portions. Current 2 is again the straight portion of the diagram, so field 2 is going to be the curved portion, or the curve of our fingers. So straight portion is the thumb, curved portion is the fingers. So we have to take our thumb and point it in the direction of I2. So take your thumb and point it down, and then allow your fingers to curve around wire 1. And as that happens, wire 1 will now have, or let me start over because I'm getting my subscripts mixed up. So we're going to take our thumb pointed in the direction of I2. Field 2 is going to wrap around wire 2, and it's going to wrap around wire 2 in such a way that the field orbits this way. So it's actually opposite of the way field 2 orbited in the top example. And that shouldn't be a surprise. We've switched the current around, so we should fully expect that the magnetic field is going to flip around as well. But as field 2 wraps around wire 2, it eventually intersects with wire 1, and its orientation is into the page. That is field 2. Okay, so we have our two currents. we have our two fields, and we can either figure out the magnitudes of the forces or the directions of the forces. I'm going to go ahead and go for the magnitudes of the forces. Again, we're using the same expression. We're using that cross product. And we're going to start with force 1, 2, which is I1, L crossed B2. And if you follow along with the stuff that we have up top there, we're getting exactly the same outcome. L is still pointing up for I1. Field 2 is still pointing perpendicular to L, so we still have a 90-degree relationship there, which is going to result in a 1 for our sine theta. So we're still getting the same magnitude of force. And if we plug in what we know about field 2 is still made up of mu naught I2 over 2 pi d. It's the same field magnitude, it's just pointing in a different direction now. And if we plug all that in, we get exactly the same magnitude of force as what we got from the previous combination. So it looks like whether these wires are carrying their currents parallel or anti-parallel to one another, we're still going to get the same magnitude of force. And just to be good physics students, we'll go ahead and confirm that with the other wire. I2LB1 sine theta. The angle relationship between L2, technically L is now pointing down with current 2, but that L vector and B1 are at 90 degrees with respect to each other. So that evaluates in a 1. And what is the magnitude of B1? Well, it's still mu naught I1 over 2 pi d. We plug that in, and we get mu naught I1 I2L over 2 pi d. So the magnitudes are exactly the same as what they were for the parallel case scenario, only now we have an anti-parallel case scenario. Do we still have the equal and opposite relationship? So we don't quite know yet what direction the forces on these wires are pointing, so let's take a moment and figure that out. For F12, first vector in the cross product is L. L is pointing up. Second vector is B2. B2 is pointing into the board. First vector is the index finger, so we point our finger up in the direction of L. Our middle finger, B2, points into the page. Our thumb thus has to point to the left. For force 2-1, and this is important now, since we've changed the direction of I2, we had to change the direction of L. So our L vector now has to point down. And our L vector is the first vector, so that is the index finger, so we have to point our index finger down. And careful not to hurt yourself, but we need to point our middle finger into the board. And the only way that I would have to stand up to do this, but in order to get that to work, the only way that we can have our thumb pointing without breaking something or straining my wrist is going to be pointing to the right. And so those two are pointing in opposite directions. and that means we have still satisfied Newton's third law. So as it turns out, it doesn't matter if the wires are running parallel or anti-parallel to each other. The magnitudes are going to be the same regardless. The only difference is whether we have an attractive system or a repelling system. In the case of the parallel currents, the wires were attractive. In the case of the anti-parallel currents, the wires are repelling one another. Now, for the attraction case, we said that the wires started pulling towards one another, and as the wires pulled closer and closer together, the separation distance got smaller, and so the force would get larger, and we'd run the risk of possibly ripping those wires out of their connection points. But for the repulsive case, these wires are going to push away on each other. As those wires push away, the separation distance is going to get larger. As the separation distance gets larger, the magnitude of force becomes smaller. And so this actually seems like a better situation, even though these two wires are pushing away from each other. The further apart they get, the less force there is, and we don't run into the risk of the two wires touching and causing any kind of a short circuit. But either case is probably not going to be beneficial to us, because what if we're constantly having to turn these currents on and off? Or what if we're constantly having to switch the directions of the currents in the two wires? Well, then we're going to see our wires effectively snapping back and forth in their connection port, and that could cause some wear and tear at the connection point, and that could cause the wires to sever. And so that's probably not something that we want to happen either. And so typically what you'll see is if there is a longer segment of wire, then there will be some kind of conduit or brace that is put around that wire to keep it from flexing back and forth like we see here. And you probably want that conduit to be made of something that's insulative, maybe some PVC pipe, but I guess if the wires themselves are insulated, you could use metal piping, but that really comes down to cost and how much your supervisor is willing to spend on a simple preventative maintenance issue like putting some kind of a brace around the wire. Alright, I think that makes for a good spot to end the video. So we've seen how two wires will affect one another. We could just as easily apply this to a system that had multiple wires. Maybe I have wire 1, wire 2, wire 3. And if I wanted to know the net force acting on wire 3, what would I do? Well, I would have to find the individual forces that wire 3 experiences from wires 1 and 2 and add them together. And I can do that by figuring out how is the field from wire 1 going to affect wire 3, and how is the field from wire 2 going to affect wire 3. So it's basically the same problem that we did over here, only we have to do it 2 times. Once for wire 1, wire 3, and again for wire 2, wire 3. But now that we've seen how the problem is worked, at this point, it's just a little bit of repetition. What I would ask you to consider is, what if we had a wire with its current running up, and then there was a second wire that was running perpendicular to the first wire, and it had its current going into the board. Would there be a magnetic force on either of these wires? And we could say, well, magnetic force says IL cross B. So is wire 2 going to create a magnetic force on wire 1? That is the question. So we'll take a look at the direction that field 2 is pointing. Now, wire 2 is not that easy to visualize because it's running in and out of the board, but we can see that its current is running into the board. And we'll assume that wire 2 is a straight segment of wire. So that means we stick our thumb in the direction of I2, and we allow our fingers to curve around wire 2. And so we're going to see a magnetic field orbiting around wire 2 in a clockwise fashion. But I need that field to extend a little bit further so that it can actually hit wire 1. And when that field hits wire 1, the orientation of that field is up. Wire 1 has its current traveling up, so there's the direction of L. But the angle relationship between L and B2 at that location is 0 degrees. Both B2 and L are pointing up. And so when we evaluate our cross product using the sine theta relationship, sine of 0 is 0. So does that mean there's no force between the two wires? Well, not exactly. What we need to do is take our magnetic field out even further, because there are going to be locations along the length of the wire where our magnetic field has components that are running parallel and perpendicular to the length of the wire. And it's those perpendicular components of the magnetic fields that I'm interested in, because with the L vector pointing up and the field vector pointing, or at least the magnitude of the field vector pointing to the right, the direction of force that we are going to see acting on this wire is either going to have to be into the board or out of the board, one of the two. And as it turns out, that direction is actually going to be into the board. And I think what I'll do is I'll do a separate video explaining how we actually get the directions that we do for these final force vectors. Because, strangely enough, when we come down to this other intersection, L is still pointing up, but now our field component is pointing to the left, and we're going to see a force coming out of the page. So it turns out that wire 1 is not just experiencing one force from wire 2, it's experiencing two forces. And those forces are effectively twisting wire 1. Half of wire 1 is being pulled out of the page, the other half of wire 1 is going to be pushed into the page. So this is a more complex scenario that we'd probably rather avoid, but we can actually avoid that by putting some more conduit around our wire. So if we put a piece of plastic conduit around wire 1, then wire 1 can't be twisted by the effects from wire 2. And likewise, we'd probably want to put some kind of a conduit around wire 2, because whatever wire 2 does to wire 1 is going to do the same thing back to wire 2 with respect to Newton's third law. Alright, so next video I'll actually go over the mathematics behind the cross product. It won't so much be a physics lecture, but we definitely need the math in order for the physics to make sense. So next video on cross products. See you then.